Hey there everyone, my name is Heenal Patel and I will be going over the fundamental theorem of calculus part 2 with you, and that's how you pronounce my name, just in case you were wondering. Anyways, let's move on. Before we start anything, I want to go over what we will be learning in this lesson. First of all, we should be able to recognize at the end of the lesson that how to evaluate definite integrals using the fundamental theorem of calculus part 2. We should be able to understand that the integral function acts as an area accumulator or net area, and then we should be able to calculate the total area between a function and the x-axis. Thus to the actual fundamental theorem of calculus part 2. Which states that if function f is continuous at every point of the interval a to b, and if the antiderivative is any, if capital F is any antiderivative of small lowercase f on the interval a and b, then this is true. So, in other words, you can also put it in this form, which will be easier. So once you find the antiderivative big F, you can say that the antiderivative big F from A to B, and then you could also put it like this. It's another way of basically saying it. Alright, and now on to our, looking at the theorem, it simply says that first we find the antiderivative of the function, and then we plug in the intervals to get the definite value. So this gives us the definite value. And then FTC2 also says that you can find an a definite value without calculating Riemann sums, as long as you can find the antiderivative. Let's do an example now. Okay, example 1 says the function f of x equals x squared on the interval 2 to 3. So first we want to put it in integral form, just to give us an idea. And then we want to find its antiderivative. Do you remember this form? Antiderivative from a to b. So the antiderivative of x cubed is 3x squared, 2 to 3. Alright, remember that if you're with powers, if you're using powers, then you should always add oh sorry, we're finding the antiderivative. I'm sorry, that's the derivative. Yeah, so when you're finding the antiderivative, you want to add 1 to the power, because when you do the derivative, you're subtracting 1, right? So you want to add 1 to the power, but then at the end you want to end up with nothing on the front. So you want to divide it by 4, because then if you derive it, that'd be 4x cubed, right? And there's no 4 over here, so just divide it by 4. You want to make sure you divide it by 4. And then you'd put it in that form. And then now we just simply plug the values, or the intervals, into the antiderivative equation. So that would be 3 to the 4th divided by 4 minus 2 to the 4th divided by 4. And if we solve it analytically, that gives us about 65 fourths, I think. And then if you plug that into the calculator and you want the actual number, it would be 16.25. Alright, so that's example 1. Before we go on to example 2, I want to remind you that you should know your antiderivative rules. Make flashcards for them and then study them, or you can use studycardlet.com. It'll just be easier for you to solve all the problems if you memorize all the rules. Example 2. If we have function secant squared x on the interval 0 to pi over 4, let's put that in integral form. Okay, you don't always have to start with putting it in the integral form, but this is just starting off. It's just good practice. You can just, once you get used to it or good at it, you can just skip to steps 2 and 3. So 0 to pi over 4 are intervals, secant squared x. And now we have to find the antiderivative of secant squared x. And if you remembered your antiderivative rules, the antiderivative of secant squared x is tangent x. From 0 to pi over 4. And again, this is from the form antiderivative a to b. So now that we found the antiderivative, all we have to do is simply plug it in. So it would be tangent pi over 4 minus tangent 0. If you memorized the radians, then you would know that clearly. I haven't, so I have to see what it means. Okay, so clearly it would be 1 minus 0, because tangent pi over 4 is 1, and then tangent 0 is 0, so then your answer would be 1. Alright, so that's example 2. And now we will do example 3, which is a little bit different because we have the square right here. So let's just put it in integral form, just to get us started here. Okay, what do you think we should do if there's a squared here? This is a question that usually, at first it really caught me because I kept forgetting to use the FOIL method. I would just do r squared plus 1, which is not right, clearly. So remember to use the FOIL method. So to find the antiderivative, first I'm going to FOIL it out, and then I'll find the antiderivative of the FOILed equation. So plus 2r plus 1. Alright, so now all we have to do is find the antiderivative of that, which is pretty easy. And it would be r cubed divided by 3 plus r squared plus r. Remember the power rule, you want to add to the exponent and divide it by the new exponent you got if there's nothing on the front of that. So now that we have the antiderivative, all we want to do is plug. Oh, sorry, we should probably put it in this form first. So a to b, right? So it would be r cubed r squared plus r in -1 to 1. So now we just plug it in. 1 cubed divided by 3 plus 1 squared plus 1. Quantity minus -1 cubed divided by 3 plus -1 squared minus 1 equal. So that should equal 8/3 if you, so that'd be 1 divided by 3, but if you, I'm pretty sure you can figure that out. That'd be 8/3, or in the calculator, if you plug it in, it would be 2.6 repeating. And now I will give you some problems to work on. So I suggest pausing the video and take some time to work on these on your own and get some practice. And then we'll go over number 3 because that one's a little different. It's not tricky at all, but it's different. So pause the video. Alright. These are the answers to the practice problems. The first one is -8.04. And you're wondering why it's negative. Let me show you the graph of it. The graph looks like that, and we are looking at the interval 0 to 1, and as you can see in that interval, the function's below the x-axis, which means it's negative, so our answer is most likely right. And then number 2 is 2. Number 3 is 16. I'd like to go over number 3 with you, as I told you before, because it's a little different. Alright, so we know that the absolute value of x function has a point of discontinuity at x equals 0. So what would we do in this case? Because we can't use FTC on functions that have discontinuity. So we would simply, what do you think we would do, actually? Yes. Okay, so we'd simply make two separate integrals. So we try to find the point of discontinuity, which is x equals 0, as I told you before. And we would make the integral negative 4 to 0, sorry. And then add it, which is the integral of 0 to 4. And if you use FTC, that would be the antiderivative, right? And then you do negative 4 to 0, which is 0 squared divided by 2 minus negative 4 squared divided by 2 minus, plus, now we want to do 4 squared divided by 2 minus 0 squared divided by 2. Okay, so this would be 0 minus 16 divided by 2 plus 16 divided by 2 minus 0. So this would be that would be negative 8. Wait, no, that's not right. That would give us 0. Anyways, I'll teach you a different approach to this problem. As you can tell, you can use geometry to figure it out, because we know it's from negative 4 to 4, and these are 4 up here, so that would mean this length is 4, this length is 4, this and this length is 4. So you would simply just use the area of triangle, which is 1/2 base times height. So 1/2, 4 times 4, which is 16, plus 1/2, 16, which is 8 plus 8, which is 16. Okay. Alright. And this is kind of like a total value problem. Sorry, no, it's not. Forget I said that. Okay, I want to give you an example of how a definite integral does not always equal total area. I'm going to graph this function for you under that integral. Zero to 3 pi divided by 2. Let's make the x scale pi over 2. Let's make this negative 1 to 1. Okay, so this is the function, and we've been doing definite integrals so far, so that means that we've been taking the net area. So if you look at this, if we did the positive area and then added it to the negative area, you know that our answer would be negative, because this negative area is so big it's going to cancel out the positive area and we're going to get a negative answer. But when we're doing total area, we don't add in negatives, so we have to use absolute value bars. Here are the steps to actually solve total value problems analytically, so without the calculator. And so you would find the area between the function and the x-axis on the interval that I gave you, the cosine problem. And then you want to find the zeros of f and then partition it, make different integrals through each of the subintervals with the zeros, kind of like how we did with the absolute value of x problem. And then you use absolute value bars with the integrals. So in this case, we would do, we know that the 0 is at pi over 2 for cosine, because it goes like this. This is pi, 2 pi, 0. Okay, so pi over 2 is where the 0 is. So we want to separate the function by 0 to pi over 2 cosine x dx plus pi over 2 to 2 pi cosine x dx. And the antiderivative of cosine is sine, so I'm just going to go ahead and use a shortcut method. 0 plus sine 2 pi and sine 3 over 2. Okay, we know that sine pi over 2 is 1, and sine 0 is 0. And then sine 2 pi is 0, and sine pi over 2 is 1. So then our answer would be 0. It would cancel out. And then I want to give you another example of the total area problem. Oh, we just did that. So skip that. Alright, so here's an example of a total area problem. Find the total area between sine x and the x-axis on the interval 0 to 2 pi. So the integral we're looking at is 0 to 2 pi over the absolute value of sine x dx. So the antiderivative of sine x is negative cosine x, and we want the absolute value of that also, or you could simplify it to cosine of x. But so let's draw a graph of cosine of x, which looks something like this being 2 pi, this is pi, that's 0, 2 pi over 2, and then 3 pi over 2. So our x's look like they're at pi over 2 and 3 pi over 2. So using the interval, we're going to make 3 integrals and add them together. So that will look like this. 0 to pi over 2 sine x dx plus pi over 2 to 3 pi over 2 sine of x dx plus 3 pi over 2 pi over 2 absolute value of sine x dx equals, you can see we're separating them by the regions. So, sorry, that region. Okay, so now that we laid them out, I'm just going to go ahead and plug these in. Sine of pi over 2 minus sine 0 plus sine of 3 pi over 2 minus sine of pi over 2 plus sine of 2 pi minus sine of 3 pi over 2. Alright, and that should give you, this should give you 1, this should give you 2, this should give you 1 again, with a grand total of 4. So that should be your area, and it makes sense because you're going to have positive area if you're not going to count the negatives. And so, and it also makes sense because this integral, or this chunk, should be equal to this integral, that chunk, which is both 1. And then this looks like it'd be double the size of this, so it's 2. So it makes sense. Okay, now if we were just doing a net area problem or a definite integral, not a total area problem, then I want to show you and compare and contrast on how the answer turns out to be different. So if it was just going to be a definite value problem, or an integral, definite integral value, net area problem, then it would be something like this. It would be 0 to 2 pi sine of x and dx, and you don't need the absolute value because it's net. And the sine function looks like that from 0 to 2 pi. So you can see this region is going to be the same as this region, and so we know that these two are going to cancel out. Finally, I want to tell you how to find total area numerically, or using your calculator. To find the area between the graph of y equals x and the x-axis on the interval a to b numerically, you use function integration. You would go to the math button on your calculator, and then scroll down, or just type, click number 9, and that will give you a function with a whole bunch of blanks. And when you're doing total area problems, you want to make sure you have the absolute value bars around the function, and then you want to put x to tell them that it's in terms of x. 'Cause when you plug it into the calculator, you're always doing it in terms of x, and then you want to put your interval into it. Some of the calculators, like I know mine, has it in regular integral form. So you can simply just type it in like that, which is much easier, I think. And this is really important to know because it could be really helpful on your AP test. Alright, so that would be the end of our lesson. And I hope you learned something from it. Bye-bye.